So yeah, thanks for having me today. Today I'm going to talk about how we are um, looking at moving toward um, using Anemoi, which is a framework for machine learning weather prediction model development. And so today I'm going to, first motivate, why we're wanting to use this tool, Anemoi, and I'll talk about some of the nice features that come along with that. Anemoi is a pretty large framework, if you've maybe heard of it or not. So part of the talk is I'm just going to introduce Anemoi, talk about what is an Anemoi, and how we're interacting with it in terms of our model development pipeline. And I'll say this again at the end, but this is really just a preview of things to come, and NOAA's contributions to this space. We're currently working to make a few aspects of this pipeline a little more ready for the public. So this is a bit of a preview. All right. This is the ECMWF logo for anyone who doesn't recognize it. So yeah, showing some partnership here. All right, so first, just to motivate Anemoi, I thought I'd talk about one of the applications that we're interested in using it for, and that's for atmospheric river forecasting. And so this figure is showing precipitable water during an atmospheric river event, and you can see this very large stream of precipitable water stretching from the tropics into the western coast of the United States. These are really large scale events that stretch thousands of kilometers. But the actual impact of the atmospheric river in terms of precipitation and flooding potential and resource management, that really requires higher resolution than we can resolve in a global model. So basically the point of this slide is just to say that accurately forecasting both atmospheric river events and their impact in terms of precipitation in the Western United States is really a multi-scale in nature. It's a multi-scale phenomenon. And so that really sets us up for what I'd say is one of the most notable Anemoi capabilities, which is just kind of pretty good default configurations for machine learning weather prediction in general. I have here, this is a bit of a snarky comment to like just fill in the data. Of course, we all know in machine learning, getting the data in place is a huge task. So it's but it basically out of the box, Anemoi has global model configurations. Also got to hand it to ECMWF for being very open. They have their AIFS version 1 configuration just open to the public. They have setups for limited area models, and then a nested or stretched grid model. And so what this figure here on the right is showing a prediction from one of our prototype nested model, where we're really developing a model to attack that multi-scale nature of the atmospheric river problem, where we resolve the globe in a relatively coarse. You can see this is actually about 1 degree globally, and then inside of this box over the contiguous United States, we want to resolve that at a much higher resolution. Right now, this prototype is just that 1/4 degree over the U.S., but we want to go sub 10 kilometer resolution. And yeah, so really Anemoi is enabling this is something I'm leading here at NOAA PSL. It's enabling that nested model development. And this is really thanks to basically Met Norway. They have a paper out where they introduce a model they call Breeze, which is Norwegian for wind, I'm pretty sure. Where they develop this setup where they have a really high resolution domain over Scandinavia, and then it's forced globally by IFS. And so Anemoi is really the community tool where they contributed all of the capabilities to do that, which is pretty exciting and lets us set up models like this. So that was just a bit of more scientific oriented motivation. Here I'll kind of just get into the nuts and bolts of Anemoi, and just reflecting some of my personal bias with some of the nice things are. But first, I just thought I'd give you a little bit of trivia for the lunch hour. Anemoi is the name of the whole framework, and this translates to the Greek god of wind. And here I just want to talk about where various parts of Anemoi fit into the end-to-end machine learning workflow. So starting up here in the top left, we have an original data source, which is what we're using to train our model. We'll go through some data pre-processing. Basically, it's usually so computationally intensive to train models that we want to pre-process the data so it's ready to be fed into the GPUs as quickly as possible. And so that's kind of creates this pre-processed data set, which which we call an Anemoi data set. And it's basically just ready to go into the ML model. With that, we'll undergo model training, and from that, we'll get our learned neural network weights. From the neural network weights, we we can carry out inference, which will give us forecasts, say over a validation or some kind of holdout test data set, from which we'll post-process the data, evaluate it, and then lots of evaluation and science really just starts there, or computing metrics, case studies, visualizing, etc. Okay, and then so this is now just showing where various parts of Anemoi fit into the program here. So during that pre-processing, basically there's an Anemoi package called Anemoi datasets that's doing two things. It's in this stage pre-processing or creating that Anemoi dataset. It's also used throughout the whole pipeline to kind of open what's the ZAR data set that's been created, but that's the key here. Then during model training, there are actually 3 Python packages that are used here. There's Anemoi graphs, Anemoi models, and Anemoi training. And so these are kind of the core, bits of functionality. For setting up the graphs, it's really a graph-based framework, creating the model, the multi-layer perceptrons, etc., and then organizing the optimizer and things like that. So these 3 packages are so intertwined that they're managed in one repository at ECMWF called Anemoi Core. They actually used to be separate, but then they figured that managing that was impossible. So then they put them all together into one. And then lastly, Anemoi Inference is a pretty lightweight package that just runs the inference. It's pretty straightforward. After that, once we've used the model, at least for now, that is the point where we leave the Anemoi framework. And for post-processing and evaluation, we can use things like, say Weatherbench, or we could use other tools there to actually carry out the post-processing and evaluation. So hopefully that gives you a little bit of orientation around Anemoi. I'll just make 2 little notes here. I mentioned, UFS to ARCO. This is a data pre-processing tool that we're working on. So this is kind of not quite ready for public consumption yet, but and then we're working on our own, a NOAA owned verification tool suite as well. Okay, and so from here, I thought I would just kind of go through some of the Anemoi characteristics that I think are nice and kind of highlight why. From a technical perspective, why we're interested in using it, and so related to training, one thing I'll say is that it's just there's a lot of capabilities that are immediately available, and especially in terms of loss functions. The one that I highlighted here is there's a stochastic CRPS loss function that's kind of more or less ready to be used, and this is as in their AIFS CRPS, which is the paper highlighted here, that contributed that and made that available. One thing that's really nice, and I can really attest to, is the easy stop and restart if your run gets canceled. And this happened to me. The machine I was using just had some trouble and killed a training job, like a multi-day training job. But I was pretty easily able to just kind of plug in the run ID and restart from the last checkpoint, which if you've ever had to kind of code this kind of stuff up, it's not impossible, but it's just really nice to have it out of the box. And with that, you can do things, kind of easy extensions from that is like, you can do things like transfer learning, you can freeze and different submodules of the model, all these kind of really nice features. Another thing that's highlighted here in the slide is that you get kind of for free lots of intermittent diagnostic plots, so you can see, monitor and watch for some red flags during the training. I've highlighted here, these are all for Z500 basically. You get a suite of figures showing, say, the inputs, the targets, prediction, the forecast error, the increment, so you can kind of compare visually the error to the increment, and then persistence error. And you can create like a whole matrix of these plots for all different variables that you want, like add 2-meter temperature, 10-meter winds, whatever. One that I really like is this histogram that gets spit out. So this is just showing a histogram of values from, one model prediction in the validation set, and spectra. Basically, like the list goes on, you get lots of diagnostic plots. It's easy to kind of catch red flags or see how things are progressing. And then there's just, lots of little easy things, like it's easy to switch between training using a maximum epoch or a max iteration. These are all kind of like small things, but when you have to code them up, it takes a while, you debug, blah, blah, blah. It's nice to just kind of have it. Yeah. So as I mentioned, Anemoi is a very graph focused framework. And so part of the model in terms of the encoder and decoder is it's assumed you generate a graph. And there are lots of different graph types that have been contributed and are immediately available. For instance, there's the multi-scale mesh that was kind of made famous by GraphCast, where you're simultaneously capturing all of these different scales and doing simultaneous message passing at those scales. They also have hierarchical meshes that are readily available from contributed from the NOAA folks. Or you can just define a single graph, say for instance, with a Gaussian grid or whatever. And it's pretty easy to generate the nodes, if you have an existing data set, or you can give, pick a given type, like a latitude longitude grid or a reduced Gaussian, heel picks, whatever mesh type, and you can very easily generate one of these meshes. You can use hexagonal or triangle refinements pretty easily for different meshes. And then so building on that, there are there are kind of different ways you can mix and match. Right now, I would say for the majority of problems, there are essentially 3 available architectures, but at least at the moment, at least from my perspective. The first is the kind of a multi-mesh graph neural network, and like this is kind of like the GraphCast style graph neural network, where you're doing a message passing processor on this multi-mesh graph. Another one, which they kind of refer to as a graph transformer, and this is the one that's used in that nested or stretched grid model called Breeze from Norway. Is you define the same multi-mesh graph, but instead of using a message passing processor, you instead use a transformer. And then there is kind of what I'm calling the AIFS style. That's what they're using in the AIFS, which is where you define a single mesh, and for them they define a reduced Gaussian grid mesh, and then use a sliding window transformer processor on that. And so this is a figure from that paper that kind of visualizes that. Yeah, so those are some of the capabilities, and then just to kind of give you a flavor for all of this, I'll show a couple of just really quick experiments that we were able to do, and kind of give you a feel for some of the comparisons that we've started to make. So the first one of the things that we were interested in is comparing some of the architectures within Anemoi, those three that I showed in the previous slide. And here we are using that nested model prototype using ERA5 data, and kind of defined somewhat representative, but not maybe a full out model to test these different architectures. What we found is by and large very relatively small performance differences in terms of skill. This is just showing RMSE skill globally here. Although we found it to not be too different over CONUS versus just looking at the globe, at least in this particular case. 2 meter temperature was probably the variable where we saw the most variability. Kind of trying to understand there, we had saw up to a 12-hour skill difference. But by and large, at least for this problem, at least for this setup, not too different in terms of skill. What we saw was really that this transformer that uses the sliding window processor that uses flash attention, which is this really optimized package for PyTorch. And in this case, it was about 10 hours, which for us was about 30% faster than the other runs. So pretty exciting to see. But I just, I want to highlight that I think these are all going to be, this is probably a case dependent plots, but what was really nice was setting up all of these three different architectures. There's a matter of just kind of getting a bunch of YAML files configured rather than going in and coding in all of these architectures ourselves. So it's pretty nice to have that just out of the box. I think that's kind of the bigger takeaway there. And then lastly, I'll just show some comparisons to the JAX GraphCast code. A little bit of context here is that, let's say a year-ish ago, when we all got started in developing our deep learning framework here at PSL and GSL together, we were pretty excited about the GraphCast architecture and took the GraphCast code base, which is in JAX. And of course, in JAX, there's no data loading or training pipeline out of the box. And so we built up all that capability ourselves. And so this left column is showing the results, just the very technical performance results from that framework. The comparison here is to Anemoi. It's not apples to apples, and so there's some key differences here. The horizontal resolution is similar, even though the data sets are similar or different. We're using the replay data set here in ERA5 here. Different number of vertical levels and also definition, although for the speed test, that's not really important. Of course, with the JAX code, we were using the GraphCast multi-mesh graph neural network, whereas with Anemoi, we're using that graph encoder sliding window model with flash attention. Different number of neural network weights, although I will say the different architectures do kind of lend themselves to having they're different architectures. So again, not apples to apples. Pretty similar number of training iterations. And before I get to these other notes, basically what we saw is that the training time is pretty comparable, I would say. We've run a lot of experiments with the JAX setup and only a few here. And so, I would just say that the timing is pretty comparable. So at least from the way that we've set everything up with JAX and stuff like that, we're seeing that JAX is pretty comparable to that flash attention performance, which is pretty interesting. Isaac, do you wanna go ahead?
Yeah, great talk. I'm just curious to know, what is your compute look like? Number of GPUs, nodes?
Oh yeah, sure. Yeah, that's a pretty critical. So the slide comes from a more internal presentation where we're all familiar with that. So it's a good point. So we're using the Perlmutter HPC machine. If you're familiar, it's a DOE machine, and that has nodes with 4 A100s on board. And we're using just in this case just data parallelism. So no, Anemoi does have the capability to do model sharding, but we weren't doing any of that here. So it's just data parallelism with batch size of 16. So
It's
16.
just a single node.
No, so we were using one GPU per sample. So it's 16 GPUs, which comes out to 4 nodes.
Okay, great. Thank you.
Yeah, thanks. That's a great question. Thanks. Yeah, but same. I'll say same compute situation for both 4 nodes, 16 GPUs, and same machine. Yeah, Marston, you want to go ahead? Is that Marston?
It looks like it's on mute, but I can't hear either. So just
okay. Drink and yeah, if you want to go ahead and pop your question into the chat, I can get to it in a second. This is my last kind of before summary slide anyway, so I'll just wrap up, talk about some other notes that I think are interesting here. As I mentioned earlier, with the Anemoi framework, you get lots of diagnostics plots that are created asynchronously, so they're not messing with your training speeds and stuff like that. So that's something we get there. We didn't code that up into our JAX code base. It's nice to just kind of get that. One thing that I think is really nice though is that inference with Anemoi is just really straightforward. It just pumps through the data kind of as you would expect. Because of the way that GraphCast is written, they use X-array and they want you to give like a template data set for your prediction. This is what I'm assuming is what's up. It can take a pretty long time to run longer inferences. Say if you're running to test the model stability like over a month or 6 months to a year. I see really different speeds. Like you cross some threshold and it takes a really long time to run that inference. Like not linear. My guess, even as I'm like a card carrying X-array fan for sure, I think this might be due to Dask issues and memory management related to hooking up to X-array. And it's obviously, I'm sure, like a way that we wrote it, but basically, like I think the overall point is still valid that using Anemoi for inference is really straightforward as well. So that's like another, I think, a good takeaway there for this comparison. All right, and so with that, I'll just end with a summary. I think Anemoi is really, I think it's a really nice community resource. Here at NOAA, we're pretty excited to use it and also contribute to it as much as we can contribute to this community. Got to hand it to ECMWF for opening up everything. They're starting to really open up their data too, and they're opening up this whole framework. And I think it's really exciting to see. I think we're going to all, as a larger community, move faster. And so, yeah, here at NOAA, we're excited to contribute into that as well. Out of the box, as I kind of showed, it's a pretty ridiculously customizable experience, and I really only kind of scratched the surface of that. And it's just pretty easy to spin up experiments, and so I think that's kind of the main takeaway of the results that I showed, is that because I think those are application dependent, is that it's just easy to make those comparisons. And so, yeah, with that, just want to give a little plug for things that are coming soon. So everything that I showed today is open source. Like you could go in and recreate everything. You could create the model that's making this flashy movie of precipitation forecasts here. However, there's some aspects that we found to be suboptimal, and especially in Anemoi's data preprocessor, we found that to not really be optimal for especially working with our NOAA data data sets in the cloud. We think it's kind of optimized for working with on-prem data, like working with our big grid store at XMWF. So in any case, we're working on developing tools to overcome this for data pre-processing and just kind of overall streamlining the experience where, we have cloud resources here. And so we're focusing on, making this available in on-prem and cloud deployments. They're just kind of these tools are not quite ready yet for public consumption. So, stay tuned for some exciting developments here. We're hoping to release these in the fall. But yeah, with that, I will take any questions. And I'm seeing quite a few come through. So thanks, everyone.
Hey, Tim, can you hear me?
I can. Hey, Marston.
Hey, sorry about that. My mic.
No problem.
Mic and chat doesn't allow me to post them. Anyway, great talk. I really like this stuff with Anemoi. I've been looking at it for a while. And I know you focus a lot on the implementation side of things, and do a great job and insight into how simple and, like you said, ridiculously customizable. But I was curious from the meteorological side, over the Amazon, some of that really caught my eye, what was going on there. It seemed kind of in a nested prototype, very broad brush in an area that can be quite significant. You showed a little bit about the what's called perception, where it
I can barely hear you. Could you speak up just a little bit?
Yeah, I was just thinking about the transformer. If it's too narrow to pick up on telecommunication, right? Things that are affecting the weather from very far away. Yeah, I was looking at that. Is that what's probably causing what we're seeing over the Amazon not to be reflected in what we see in Era 5?
Oh, okay. Yeah. So very, very astute observation here. That's great. Exciting to be talking about science here and development. So that, yeah, over the Amazon, it does look pretty crazy. You're right. It's like way overactive. I think, so that the model that I'm showing here is actually using the graph transformer style with the multi-mesh graph and with the transformer. So not the sliding window here. I think it could be, it's just kind of an early prototype, so it could be a host of things. It could be, I don't know. I don't want to get too, it could be a number of things. Let's say I'm focusing the loss function over the US. And so kind of like de-weighting the rest of the globe. Maybe I did that a little too much. It's also undertrained. So that could be part of it. I didn't carry out any like multi-step rollouts that could help with what's going on there, because this is showing a 10-day forecast in that figure. It could just be the fact that in the figures here we're looking at quarter degree Era 5 here on the left, and on the right we're looking at that in a conservatively regridded 1 degree. So there's different resolutions. Different resolutions, that's right. And so eventually we do want the global forcing to be quarter degree, but
I was noticing that it over the US it wasn't being a broad brush. I mean, it was really following the Era 5 as well, but there over the Amazon. Anyway, great talk.
Thanks. Yeah, and that's just kind of, we just want to capture the global forcings and then really resolve here. But thanks. That's a great question. Let's see. I will go ahead and got 2 questions in the chat that I'll take. Okay, from, if I recall correctly, Anemoi requires the input data to be pre-processed into a specific structure in ZAR. How much of a barrier is that? Yeah, that is like, that's a great question. That's kind of one of the main barriers in the whole pipeline. And that's really the reason that we're working on this tool, UFS to Argo, to pre-process that data. And so that's what we're doing is we're taking data in a variety of forms, say like a zoo of GRIB data from like NOAA's GFS archives, or we could take a ZAR store that's up in Google Cloud, like the Google Cloud Era 5 record, for instance. But we just have to put that in that, that ZAR data set form that's kind of ready to go into the ML model, just like what you're talking about. So the current Anemoi data sets, it works, but yeah, I've found it to be extremely slow, hard to parallelize. And I don't like say that to diss on ECMWF at all. It's just like, it's a hard pipeline, and it's very often the case that when you take a workflow that works really well on-prem, it just doesn't scale to cloud, cloud-based workflows. It's just the way it goes. It's different bandwidth latency issues. So yeah, right now we found that to be a barrier, and so stay tuned for more to come on that one. Feel free to pop up if you have more to ask there, but I'll go on to the next question. Does it need to spin up before the actual forecast? So no, this is in an autoregressive model. So it takes, in the case of the models that I've been showing, it takes 2 input initial conditions, and then you're off to the races. And so it's kind of as spun up as your data is. Hopefully that gets to your question here.
Great. I just double checked Slack and in the channel. I think that's all the questions. So yeah, thank you very much, Tim. This was a great talk. And pending any other questions, we'll move on to the next one. So thanks, Tim.
Hey, yeah, no problem. Thanks for having me.
Next is going to be Justin Andrew. If you can throw yours on. We're going to be doing a brief demo and first basically what we just saw. So yeah, giving credit to Tim here as well. So thanks, Tim, for assisting Andrew with some of the work to build this. But without further ado, I'll turn it over to Andrew. Thanks.
Cool. Thanks, Kevin. Yeah, so this is going to be a little bit of a demo running through the Anemoi training workflow. Before I get started, Tim mentioned UFS to ARCO for generating the data sets. So in this notebook, we already have that done. We're going to be downloading a zip file I put together that already has the data set in it. But using UFS to ARCO to make the data sets is extremely easy, which is another really good benefit of running running this framework. So if you open up this notebook, and I believe the link was provided on the agenda, you'll need to run this on an A100 instance and then set up your environment. And then I've already gone through and done this ahead of time, I believe. I have not actually. But basically, we have this zip folder on S3 that contains all of the files that we will need. So I'll just retrieve this really quick. And so there's a bunch of YAML files that are included by default in Anemoi that you can easily go in and modify. And so while we're waiting for this to download, it's going to unzip it, and you'll see the directory structure show up here, if it ever wants to show up. Okay, I am not sure why this is taking so long. This usually takes about 30 seconds.
Yeah, no problem. Just add one piece on, Andrew, while it's running for a second here. I'm going to go ahead and put a link in chat to all the AI notebooks that you see today. They'll be available via this GitHub, and I'll pin it as well.
Try to stop and start again.
Yeah. Here, let me nuke this. There we go. Okay. So you get this really complicated directory structure with all the YAML configurations in here. And then the data set, which is created with UFS to Arco, is already included in here. There's a training, validation, and testing data set, each of which only have 2 days of data, just for the sake of running the demo. So the model training is done using the Anemoi training module, and the link to that is provided in here for more documentation. But 2 days of data in the training, validation, and testing data set on this. So you need to configure a couple environment variables before you begin training. So Anemoi requires a base seed. So this is for model initialization, initializing the weights, etc. And then it also needs a Slurm job ID. Even if you aren't running this on Slurm, you can just simply pass like a 0 into the Slurm job ID, and then it'll run just fine. And then you can also use the Hydra package, which allows you to basically get more. You can set this environment variable to get more detailed traceback information, and this is helpful for debugging, and it's helped me out quite a bit. So when you train the model, first of all, in this cell that I have down here, there's a few parameters you can configure, like the batch size, the number of channels in the model, and the number of layers in the model processor. You can simply just put all of this into a YAML file, which is really nice because you don't have to, put 100 arguments in the command line. But you can also override some arguments via the command line as well, which is what I do here by putting these parameters in here. But if we run this will train the model for 3 epochs. Should take between 4 and 5 minutes. But you can see everything that it's doing here. It's going through some sanity checks. It shows you where the output is going. So yeah, this will take about 4 to 5 minutes. But it's really nice because you can easily override some arguments via the command line, so you don't have to go digging through the YAMLs. But you can also, if you have a configuration that you have already set up, you can just simply call the config file with this and then run the Anemoi training train. Oh, and I forgot to set the environment variables. Yep, that might help. But you can call the model config file, and if you don't override anything, it'll just take all the arguments from that config file and then train the model with those arguments. So we have 4 to 5 minutes to 4 to 5 minutes to kill. But while this is running, it's going to start outputting some asynchronous plots, as Tim was mentioning. So we'll see some of that once the model actually starts training. But you can see it's outputting a bunch of information. The model has 5.4 million parameters. And now it's going to start training. This will not take very long because it's only 3 days or only 2 days of data in the training and validation data sets. But we go down to this folder here, and all these model runs are saved with basically a hash identifier. So it's a random hash to identify each model run. And if you go down to here, I can't show these on Google Colab for some reason, but there is some information about what the model is outputting. There's some information about the loss with the model, and then also there's some sample plots as well. So you can see all of those filling in actually in real time, which is super nice because then you can tell whether or not your model is working from the get-go, so you don't have to spend the entire time waiting for the model to train in order to know if it's doing something correctly. You can just look at this, the information in these plots, and figure out if your model is actually doing what you expect it to be doing or not. So it's already done with the first epoch. There's only 2 more left, and then we will get onto inference. But in the meantime, are there any questions about this? Yeah, Amir.
Hi, I just wanted to know where can I access this notebook?
So I think Kevin, you said you're gonna put the links in the chat for the notebook.
Yep. So this notebook is the only one that isn't. It's going to go in the link in chat. So I'll put it in just one more time here. So yeah, great question. So it'll be in NOAA Epic AI notebooks. The other two we have later today, and then Andrew will put this one in just right after this talk. So that will be in there as well.
All right, so we're getting through the second epoch here, but you can see it's still outputting more of these plots here, so you can see what's going on in real time, which is super nice because personally, me, I like knowing if the model is actually doing what it's supposed to be doing before before I wait a whole day. Yeah, John?
Yeah, can you just explain? I think you said it only runs on A100s if that's like a small fee, right, through Google Colab?
Right, yeah, you have to use compute units. Unfortunately, with this, you need the flash attention module, and that only runs on NVIDIA Ampere or newer GPUs, which is like 2020 and onward. So like a T4 GPU, which is free on Colab, but that won't work. So you do need to run it on like an A100 or something newer than that. Yeah, Kevin?
Yeah, and just to add one piece on there. So yeah, we're going to kind of just go over that in my talk later today. But it's basically like $9.99 for 100 credits to run that. Just gee whiz for anyone out there. So if you go to the top right and you click on it, CPU and T4 GPUs are as well as V28 TPUs are the three that are included in the free tier. And then there's like 6 more that are included in the pay for tier, and it's 100 credits for $9.99 to run that in. When we look it up, Andrew, you can run it about 10 times for one paid for credit of $10. Is that about right?
Yeah, it's not. It doesn't use very much. So yeah, it uses about 7 credits per hour. So I've ran this quite a bit, and I've only gone through 16 compute units. So it's pretty reasonable. Okay, yeah, so the model training is now done. And so now once you have your model and it's done training, you can move on to inference. So first off, the model runs are actually saved, as I mentioned, by like a hash identifier. There's not really any orderly way to, or any orderly structure to it, to the model run specifically. So we can just run this cell and get all the available model runs. So this one is the one that I just ran. So if I copy that and then put this down here, we can load the model checkpoint, which is basically the last point where the model saved its weights. So we can get the latest version of that, load the checkpoint. And then as Tim was alluding to in his talk, the inference is extremely straightforward. All you have to do, and you can use a config file for this, I believe, but you can also just run this straight from the command line without many arguments. So all you need to do is pass the checkpoint, the dates, so the initialization date, the lead time, and then the actual data set you are using. In this case, we're going to be using the testing data set. And then you can pass in a netcdf output variable as well, so that it will output the model inference into that file. So if we just run this should only take a few seconds here. So right now it's actually predicting an 18-hour lead time, and it is done. So if you look over here on the left side, you have the forecast.netcdf. That is your model forecast. So that is actually pretty much all I have for the demo. Yeah, training these models with Anemoi and then running the inference is extremely simple. You don't need to configure a whole lot. So yeah. There's any questions?
I mean, just to add to that, you said training is simple. I mean, it depends upon how much data you want to train with.
Right. Yeah. I mean, it's more simple than, say, building your own model, which is like what I've done in my research. You can simply change a few arguments in the YAMLs to call different model architectures. think we have one hand raised. Yep. Oh, I thought somebody had a hand raised.
Yeah, Jong-hoon, did you still have a question? There was one hand. Okay, if anybody has any questions, we have time for about 1 or 2 questions. If not, thank you very much, Andrew. That was great.
Yeah, thank you.
Can I ask something quickly?
There's actually 2 now. Yeah, go ahead, Amir.
So it's just again about the notebook. I guess you guys mentioned it's going to be uploaded somewhere, but it's not uploaded now, right?
Sorry, I had a hard time hearing the question. Can you repeat that?
So you guys said that the notebook is gonna be up somewhere, but it's not uploaded right now, right?
Yeah, so we can share it from here. It'll be uploaded in just 5 minutes. It'll be at that link to answer your question, Amir.
Okay, thank you.
Yeah, and then there was a question in the chat about, do the lead times only go out to 18 hours? No, they go out. In this case, we only have 2 days of data in the testing data set. So that's why I had such a short lead time here. But if you had a much larger data set, you could run it out, 240 hours or longer if you wanted to. But the only reason it's 18 hours in the notebook is because the testing data set only has 2 days of data in it.
Great. Any other questions? Otherwise, yeah, thank you very much, Andrew. Okay, hearing nothing, you can stop sharing your screen and appreciate it.